Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss wave velocity, particle velocity, relation between wave velocity and particle velocity, and differential equation of wave motion. Let's begin. Wave velocity is the velocity with which wave progress through that of medium is known as wave velocity. So, how wave propagates through that of medium? As the wave propagates, the crest and trough, in case of transverse wave, if we take transverse wave, so that plane progressive wave travels look like this. This is the crest, that is the trough, and in case of longitudinal waves, that in the form of compressions and rarefactions. For longitudinal waves, just like this, compressions and rarefactions, travel with wave velocity. Since the particles at the crest or at the trough are in the phase, look that particular graph. If the particle is at crest, so it has the phase here 0, here phase pi by 2, here pi, here 3 pi by 2, here 2 pi. So the particle at crest is the phase pi by 2, when that particle is at the trough at the phase of 3 pi by 2, means the particle with crest or trough are in a particular phase. We can say that the phase travels with the wave velocity. Therefore, that wave velocity is also called the phase velocity. That wave velocity is also called the phase velocity. That is the wave velocity, the velocity at which the wave progress in that of medium, and also that wave velocity can be considered as the phase velocity. Again, there are another key points regarding wave velocities. So the key points, right, the wave velocity through a given medium is constant. Constant means if the wave velocity in air, throughout that of air, the wave velocity is same. If we consider water, again the wave velocity is same throughout that of water medium. For a given medium, the wave velocity is constant. Another key point regarding wave velocity, it depends on the nature of the medium. It depends on the nature of the medium. But does not depend on time and the source where it produces. Depends on the nature of the medium, but independent to that of time and so source where it produces. Mathematically, the wave velocity or phase velocity written as v is equal to omega by k, where omega is the angular velocity, k that is the wave number. Since we know the angular velocity omega is equal to 2 pi nu, nu with the frequency, nu that is the frequency, and wave number or propagation constant k is equal to 2 pi by lambda, where lambda is the wavelength. Now we put the value of omega and k in that of expression. Therefore, wave velocity v is equal to 2 pi nu divided by 2 pi lambda. By solving that one, we get v is equal to nu lambda. V is equal to nu lambda. That means the wave velocity is equal to the frequency into wavelength. Wave velocity is equal to frequency into wavelength. Here the wave velocity is the velocity at which a plane wave advances with constant phase. Thus, the wave velocity is the velocity at which, in that particular velocity, a plane progressive wave, or we can say it as the travelling wave, a plane wave advances with constant phase, that constant phase be omega t minus kx, as y is equal to a sin omega t minus kx is the equation of plane progressive wave, that is the equation of plane wave. So here omega t minus kx is the phase through which that velocity travels. If the phase is constant, if phase is constant, then what happened? The differentiation of that phase with respect to time will be 0, or d by dt, the phase omega t minus kx is equal to 0. Its differentiation, that is omega minus k dx by dt is equal to 0, or k dx by dt is equal to omega, or dx by dt is equal to omega. In place of dx by dt, dx, that is the wave velocity, dx by dt is the wave velocity, that is wave velocity v is equal to, it is omega by k, as we mathematically write it. The wave velocity is equal to omega by k. Here the term dx by dt is the wave velocity. Wave velocity, which is known as the phase velocity. Some key points regarding wave velocity, its mathematical representation. Next, particle velocity. In a wave motion, as we consider the propagation of wave, in that particular wave motion, the particle is at its own position, not travelled. So, the individual particles which make up the medium do not travel through the medium with the waves, they simply oscillate about their equilibrium positions. They do not travel with the waves, so what they perform? They simply oscillate about the equilibrium positions. So, we can calculate the instantaneous velocity of an oscillating particle of the medium through which the wave is travelling is known as the particle velocity. So, mathematically, if we take a plane progressive wave, equation of plane progressive wave, or we can say that is the travelling wave, y is equal to a sin omega t minus kx, where a is the amplitude, as all terms we know omega t minus kx is the phase, omega angular frequency, k propagation constant, y is the displacement. So, the velocity we obtained, therefore, particle velocity u is equal to the rate of change of displacement dy by dt, that is d by dt of a sin omega t minus kx, that term, or u is equal to a omega cos omega t minus kx, that is the particle velocity. So, the particle velocity will be maximum when that cos term is maximum. So, u max is equal to cos maximum value of cos omega t minus kx is equal to 1. At that particular case, the particle velocity will be maximum, that is equal to a omega. Similarly, we also calculate the acceleration of that particle which vibrate in that particular medium. The acceleration of the particle, vibrating in that wave motion, that is a, that is rate of change of velocity du by dt, that is d by dt of the value of u, that is a omega cos omega t minus kx. Its differentiation with respect to time, a is equal to minus a omega square sin omega t minus kx, or a is equal to minus omega square a sin omega t minus kx, that is the value of y, it is y, that is the acceleration of that particle when that particle is vibrating in that of wave motion. Again, the acceleration is maximum when the displacement is nothing, the amplitude of that of wave. At that of condition, the acceleration, we get maximum acceleration when y is equal to a, that is minus omega square a. When y is equal to a, that is the amplitude a. At that particular condition, the acceleration of that particle is maximum. It's particle velocity, that is wave velocity. Now we draw the relation between particle velocity and wave velocity. The equation of plane progressive wave, equation of plane progressive wave is given by y is equal to a sin omega t minus kx. Y is the instantaneous displacement of that of particle at the point x in that of medium, and that expression indicates. So the instantaneous velocity, therefore we calculate instantaneous velocity, which is u at the point x, is equal to del y by del t, del y del t of a sin omega t minus kx, or u is equal to a omega cos omega t minus kx, that is equation number 2. Now differentiating that equation number 1 with respect to x. Now differentiating equation 1 with respect to x, we get del y by del x equal to del by del x a sin omega t minus kx, or del y by del x equal to minus a, its differentiation k cos omega t minus kx. And equation number 3. Let we divide that equation by this equation, dividing equation 2 by 3, we have, that is u divided by del y by del x, that is a omega cos omega t minus kx divided by minus a k cos omega t minus kx. A cancel out, cos omega t minus kx, cos omega t minus kx cancel out. So omega by k is the value of minus omega by k. Again we can put the value of omega, that is minus 2 pi nu divided by k 2 pi by lambda. Under solving it we get, that is nu lambda, frequency into wavelength, that is the velocity v. Therefore we have u by del y by del x is equal to v, or u is equal to v into del y by del x, and the negative sign here, and the sign is negative. Write it as, that is minus nu lambda equal to minus v, minus v, minus v. U is the particle velocity, v is the wave velocity, and del y by del x, that is the slope of displacement curve at point x. So we have particle velocity, which implies particle velocity at x is equal to negative of wave velocity into slope of displacement at x, slope of displacement at x. Here the particle velocity at x, u, that is the instantaneous velocity. So that is the relation between particle velocity and wave velocity. Now the differential equation of wave motion. Similarly, we have to consider a plane simple harmonic wave that traveling through a medium along x directions. Therefore the equation of plane progressive wave, equation of plane progressive wave, y is equal to a sin omega t minus kx, as usual. Now differentiating that equation with respect to time t, differentiating equation 1 with respect to time t, we get del y by del t is equal to del by del t for a sin omega t minus kx, or del y by del t is equal to a omega cos omega t minus kx. Again differentiating with respect to time, again differentiating with respect to time t, del square y del t square is equal to del by del t of that value a omega cos omega t minus kx, or del square y by del t square is equal to minus a omega square sin omega t minus kx. Let it taken as equation number 2. Now differentiating that plane progressive wave with respect to x. Now differentiating equation 1 with respect to x, we get del y by del x, that is del by del x of a sin omega t minus kx, or del y by del x, that is minus a k cos omega t minus kx, which differentiation with respect to x. Now again differentiating that with respect to x, again differentiating with respect to x, it is del square y del x square, so del by del x of that term minus a k cos omega t minus kx, or del square y del x square is equal to minus a k square sin omega t minus kx. That is equation number 3. That is del square y del t square del square y del x square. Now dividing equation 2 by equation 3. Here dividing equation 2 by 3, we get del square y by del t square divided by del square y del x square is equal to the value del square y by del t square minus a omega square sin omega t minus kx divided by that value minus a k square sin omega t minus kx. So negative negative and a and a cancelled out. So here we have omega square by k square, therefore omega by k whole square, omega by k whole square, that is v, wave velocity v square, or we have that value del square y by del t square is equal to v square into del square y by del x square, that is del square y by del t square, del square y by del x square. Here I just write it. It is del square y by del t square divided by del square y by del x square. Therefore del square y by del t square is equal to v square, that is v square into del square y by del x square. That equation, that is the differential equation of wave motion. This is the differential equation of wave motion. Differential equation of wave motion, or which is also known as classical wave equation. Classical wave equation. Classical wave equation. Del square y by del t square is equal to v square into del square y by del x square. V, that is the wave velocity. So, with the help of this video lecture, we understand what is wave velocity, which is known as the phase velocity, some key points, and its mathematical representation of wave velocity. Then particle velocity, its mathematical representation, and acceleration of that particle, relation between particle velocity and wave velocity, the relation between particle velocity and wave velocity, and differential equation of wave motion. First we differentiate that equation with respect to t twice, then differentiating that equation with respect to x twice, and dividing these two equations, and finally we get a differential equation which is the equation of wave motion, or we can say that is the classical wave equation. So, with this useful and informative notes, let me wind up this session. Thank you.